All right. So what I wanted to do here was first go over from yesterday's discussion about the binomial option pricing model, um, the derivation of the formula for P, the probability of moving up on the binomial tree. And of course, that would imply the value of 1 minus P, which is the probability of moving down. So we already know how this framework is set up. And so keep in mind that this binomial option pricing tree is designed to replicate the Black-Scholes model. And then in addition to that, provide us with the ability to price American options. So what's happening? Why is this formula P, the one I showed you yesterday, why is that correct? So remember, we saw that it is equal to that would mean that okay. Well, where did that come from? Well, first of all, let's remind ourselves what these mean. R is the risk-free rate of interest. Delta T is the time step between, no, there's a time that evolves from one time step to the next. So if you had, for example, a 1-year call option, and we set up our tree to have 2 time steps, that implies that delta T is half a year. All right, so it's because it's a 1-year call option, that means with only 2 time steps, each time step must, of course, be 6 months or half a year. Then we also have U and D. U is the size of an upward movement. And we saw yesterday that in Cox-Russell-Rubinstein's model, that is equal to e to the sigma radical delta T. And then D is the inverse of that, the size of a downward movement. And this, by the way, applies to the stock or underlying asset, not the option. Okay, the option does not move up and down by a constant amount. And that therefore would be e to the minus sigma radical delta T. Okay, so this is the mystery part. Where did this come from? This is the price, the probability moving up, and the 1 minus P obviously is the price, the probability rather of moving down. Okay, so here's what's going to happen. So in the slides, I have an example of this based on a single period model, which is fine. You can see here that this is what it would look like. Now, here we're going to use K for the strike price. Okay, so this is a call. You can tell because when the we go up the branch, we reach max SU minus K0. So that means going on behind the scenes is a stock price tree. USSU actually, it means the same thing here. I see that it's SU. I'll tell you what, let me draw this again, just so we can be consistent with yesterday. I just want to make sure everything is the same as what we were saying yesterday. This is what we're going to have. This is the stock. We only have one period. We only need one period actually to prove what we're about to do. Okay. So you remember from yesterday that since this is a one period model, the option value at maturity is always equal to the payoff. I'll just stick with X because we used X yesterday. And then down here we have max DS minus X and zero. Now, here's one of the interesting things about what we're about to do. The probability we saw yesterday is referred to as a risk neutral probability. It is not, you'll be shocked to hear, the actual probability of an upward movement. And so in order to illustrate that, we're going to let the letter G represent the real or actual probability of going up, and 1 minus G is down. And what we're going to prove here is something very surprising. We'll call it the real world probability of an upward movement. Price of the option is independent of the choice of probability measure. So in other words, when you get to the end and you look at the price, you'll see that P doesn't appear anywhere. Neither does G. So in other words, the probability is not actually affecting the price of the option. So and what does this word risk neutral mean? All right, well, risk neutral means the risk preferences of investors who are indifferent to risk. And what does that mean? It means that they would accept same return from risk-free or risky as risk-free assets. Okay, so in other words, imagine the following situation. Suppose that a treasury bond has a yield of, let's say, 4%. Actually, I should have specified a 30-year. A corporate bond rated, let's say, double B, which is very bad, by the way. In reality, typically offers a much higher coupon or a higher yield to compensate investors for their risk. Suppose that in this case, the yield of double B bond is, let's say, 10%. Now, in economics, we have three basic categories of risk preferences, as they're called. All right, so here's how this works. Risk averse means investors require a higher return to invest in risky assets. Well, you figure, well, what else could there possibly be? And by the way, what's interesting about this is that not all investors are equally risk averse. Some are terrified of risk, and some of them are not scared of it, but they still require more compensation to hold a risky bond versus a safe bond. But all of them can agree on one thing. All across the board, all these risk averse investors can agree we must have a higher return in order to buy a risky bond. The question is how much higher. Nobody in the right mind, in this group at least, would buy the triple B or double B bond if it only offered a yield of 4%, let's say. But then the risk neutral investors who do not require a higher return, to invest in risky assets. Wow. So in this case, they would accept a yield 4% from the double bond. Wow, that's interesting. And then we even have a third possible category called risk-seeking investors who enjoy gambling so much who would actually accept a lower return. That's the risky assets. Wow, in this case, they might accept a yield of 3% from the double. Of course, these are all theoretical categories. Nobody's saying that this is what happens in the real world, but it is the way that economists can classify different attitudes towards risk. And so the interesting thing is, if we did find an investor who was risk neutral, is that the investor would accept a risk-free rate of return from all assets. Now, here's the interesting part. In the Black-Scholes model, price of the option is the same, no matter what assumption is made about risk preferences. So therefore, the model uses the assumption of risk neutrality because it avoids the need to estimate risk-adjusted rates of return. In other words, the cash flows from all assets can be discounted at the risk-free rate of interest, which, if you remember, is simply the yield on treasury securities. And that makes things infinitely easier for us. So you'll see that in this framework, the probabilities that we choose are based on the assumption of risk neutrality, which means they're going to be different than the real world where people presumably are risk averse. So what we're about to do is see how we can prove this. So we start with this setup where we have G, which is real world risk, the real world probability of an upward movement. We're going to see that the results are the same whether we use G or P, the risk neutral probability. How can this be though? All right, well, let's see how this can be. The first thing we need to note is that this is all being done to replicate the Black-Scholes model. So what we're going to do is show how the price of a call can actually be replicated, assuming that it's written on a stock in the following interesting way. The cash flows to a call option at any point in time can be replicated by portfolio consisting of the underlying stock and the risk-free asset, meaning a treasury security of some kind. But the key to the whole thing, though, is that cash flows of the call option and this portfolio, just forever now going to be known as the replicating portfolio, will only be the same if the quantity of the underlying stock asset are correct. In other words, you can't just blindly buy a bunch of stocks and risk-free assets, meaning treasury securities. You have to have the right ratios. And then if you do though, then you can show that the two will be the same. And why does that matter? So if we can show that the correct weightings, the replicating portfolio results in exact same cash flows as the call option. It must be true that today, price of the call equals the price of the replicating portfolio. Otherwise, as we've already seen, there will be an arbitrage opportunity, meaning that we would buy cheaper of the two and sell it for expensive. In the process of exploiting this arbitrage, the prices of call and the replicating portfolio adjust until they're equal. So the question is, how do we come up with those weights? Where do those come from? All right, so here's how it's going to work. We're going to start by saying F, the call price, the value of the call. Now, if you notice, we still don't know we're going to solve for these by solving simultaneous equations. We have 8 shares of the stock, which we don't know what that is just yet. $B worth of the treasury securities. So this is not a number of bonds, it's the dollar amount. Okay, so how do we know? Let's prove this. And H is referred to as the hedge ratio. So that being the case, the price of this portfolio is HS plus B, meaning that we have 8 shares of S, the stock, and B dollars worth of the bond. Okay, so that means okay, let's see if we can get Word open here. So actually we need 3 trees for this one. Now in the upstate, if the stock goes up, the stock will be worth US. Now the bond will earn the risk-free rate of interest. So its future value is okay. And then down here, all right. How does that help? Because that means we can set these equal to each other. You can see that now we'll have enough information. We can solve for 2 simultaneous equations. We're going to solve for H and B. And so the portfolio has 8 shares of the stock, which, by the way, we're allowing for the possibility that it could be fractional, a fractional amount. We're also allowing for the possibility that it could be negative. So in finance, there's a way we can carry out something called a short sell, where we're actually selling shares of a stock that we don't own. Of course, eventually we have to replace them, but it can be done. So negative number of shares is not that bizarre. Anyway, so let's see what this turns into. Now, the way it stands right here, it's going to be a mess. I'm just going to jump ahead and show you what the results are. Yeah, let's speed things up. I just showed you. Um, okay, let's give this a minute or two. Here we go. So, and then the dollar value of the bonds would be. So, if you want to work through all the time, if you, it's really, let's just say it's a lot of work, but this is the final result. Now, that means that we know that F must equal HS plus B. In other words, the price of the option is the same as this replicant portfolio today in order to avoid arbitrage. So we have F equals HS plus B. And we know that again because we know that their cash flows will be the same in the future. Now we plug in these two terms that we just created, and when all the dust settles, this is the final result. And again, if you want to work through all the tedious algebra, you can certainly feel free to do so. And you'll see that you have this. We saw this a lot yesterday. Now, what's interesting about those two terms, you can think of it as the weights of FU and FD. Each one individually, um, because of the way that U and D are defined, both of these terms are bounded between 0 and 1, and of course they add up to 1 as well. They satisfy all the properties needed for probability. So in other words, these two expressions could be thought of as probabilities of some type. But here's the important part. What kind of probabilities are they? Well, keep in mind that when you look at your stock tree, by the way, S delta T means the price of stock delta T in the future. That's notation is a little different, but so the expected value of the stock at time delta T is the probability of going up in US plus 1 minus P DS You can see that because it's P to go up, 1 minus P to go down. So the expected value is what you're seeing there. And if you're now plug in those two expressions that we just saw for P and 1 minus P, you get an extremely interesting result. And again, we'll skip over all the messy algebra, but if you do, we'll end up with this expression. And this is the key to the whole thing right here. Those two probabilities, whether they describe the real world or not, here's what they produce for us. The result here is that this is the future value of the stock. When invested at the risk-free rate. If you sold the stock and collected S dollars now in one time period, and you use it to buy a treasury bonds, this is what it would be worth one period in the future. And remember, this is what Ford said earlier, describes risk neutral investors. They are willing to accept, on average, the risk-free rate of return from their investments. So that means that these two probabilities we just saw can be interpreted not only as probabilities, but as risk neutral probabilities. They are the only probabilities consistent with risk neutrality. And since we got through saying just from before that the value of the option is independent of risk preferences, we can make any assumption we want about risk preferences. Therefore, we will choose for convenience risk neutrality, and therefore these are the probabilities that we use on the trees. Okay, so that's where they're coming from. These are risk neutral probabilities, and they're used to assume that investors are risk neutral, which we are here. Wow. Okay. Now another branch of the finance, you wouldn't get away with this, that's for sure. But here, because these are derivatives, their values do not depend on risk preferences. We can do this and come up with the correct results. And we can show that if, results that we have are enforced by the lack of arbitrage. All right. So that's the argument of those mysterious probabilities. So I wanted you to see how that works, understand that all option pricing theory is based on this notion of risk neutrality. In fact, all derivatives are priced this way. They're all based on the assumption of risk neutrality because the results are independent of risk preferences. Because, and again, in turn, because if you can replicate the returns to an asset with another portfolio of assets rather, then nobody's opinion makes any difference about their value. Okay, anyway, it takes a while to get used to this idea of risk neutrality, but and you notice it doesn't matter if this is happening in the real world or not. It's not going to affect the results of our option pricing models. Now, here's what we need to do now. We're going to jump ahead to this last topic. We don't have really time to investigate the trinomial option pricing model. It's basically an extension of the binomial option pricing model where we have a third branch in the tree. And for some types of applications, that gives us more power and flexibility, but it's a lot more complicated. Instead, I want you to make sure that we cover Monte Carlo simulation, at least introduce it, because it is a very interesting way of getting at results without having the requirement of a rigid model. Instead, we're basing all of it on assumptions about the statistical properties of the assets that we're pricing. So, Monte Carlo simulation. So we're going to just touch on this. I mean, it's a very deep area of study. And I did mention, I think yesterday, that this approach is very useful for pricing what are called exotic options. Now, before we go any further into Monte Carlo, I would like to at least show you what I mean by exotic, or at least a few examples. Okay, so it looks like that the Monte Carlo notes are not open. I have the exotic options file here, but not Monte Carlo for some reason. Here we go. Oh, no, there it is. Okay. So, oh yeah, so here's the Monte Carlo notes, but I wanted to briefly introduce you to the so-called exotic options. They're kind of interesting. And you might think, well, why do people buy these? Well, they have very specific needs. They're trying to hedge some very strange situations. And there's quite a few of them. You've got forward start options, which start at some point in the future. You can think of it as an option on a forward contract. Compound options are options on other options. Future option is one that lets you decide in the future whether or not you want your option to be a call or a put. The one I want you to really see here, because you'll find this very interesting, I think, is the so-called barrier option. There's more here too, but the barrier option, I think, is one of the more interesting ones. And you're going to see exactly what it means to be exotic when you see this thing. So um, you might be hard pressed to figure out why you would want to use this thing, but it's good to know that these exist. So a barrier option, similar to a European call or put, depending on how you set it up, except that the value depends on the entire history of the stock price, let's say, during the lifetime of the option. Not just what is it equal to at the maturity date, but the entire history during that the lifetime of the option. It is therefore said to be path dependent. So in other words, now let me show you what I mean by that. So imagine you're watching this option. So time is elapsing. All right, let's wake this thing up. This is the price of the stock underlying the option. Now here's time zeros today. And let's say this is the maturity date. I'll call it capital T. At zero means the initial price of the stock, and it floats around. And here it is on the maturity date. So let's just say that the strike price for a European call option is here. So the maturity date, the payoff, is equal to, since it clearly finished in the money, S0 minus X. Wonderful. And we're all happy. We got a positive payoff. Now, if instead this had been a barrier option, now there's many ways of structuring a barrier option, but let's just say that it's chosen to be set up like this, with one addition, one key addition. I'm going to set up, in addition to the strike price, I'm going to have what's called a barrier. And if you notice right here, stock price reaches the barrier. So what does that mean? All right. So if this option is set up as a knock in knockout option, then it will have the same value as European call if stock price never reaches the barrier. Otherwise, it will have a value of zero. Meaning it's knocked out. Now, if this option is set up as a knock-in option, we can put yes for this result. Then it will be worth zero unless the stock price reaches the barrier. Then it will have the same value as a European call option. In other words, the option is knocked in. So whether it becomes valuable or not when you reach the barrier depends on whether it's a knock-in or knockout option. Wow, that's bizarre. So you can see that while if this was a European call, we definitely get a payoff. Whether we get a payoff here depends on whether it's a knock-in or a knockout. Okay, so you can see why it's called a path-dependent option because it's not just where did we end up, but how did we get there? That starts to affect the value of the option. Now you can see there's no way that Black-Scholes can handle this, and neither could the binomial option pricing model. We need something different. Now, Monte Carlo is really well suited for modeling path-dependent options because, as you'll see in a bit, it is based on paths. And what we're doing is simulating paths for the stock price, and then we use those to calculate the price of the option. Okay, so in other words, with Monte Carlo, we're going to use statistical methods to do something like this. Oops. Yeah, that's right. That's time. So in other words, here's stock price now. And we're going to not observe the price of the stock. We're going to simulate it. Here's the first path. Then we go back and do it again. Here's path number 2. And then here comes path number 3. And path 4, etc., etc. Okay. When you're done, what you have on the maturity date this procedure produces a probability distribution for the future value of the stock. So what we're going to do is now we're going to assume that each one of these paths is equally likely to occur. So average the payoff, let's call this say, to the option is calculated as, and let's assume that it's a call. Okay. S average minus X 0. Okay. And then the call price itself is the present value of this average payoff. Wow, that's interesting. Now, the only unfortunate part is if you notice here, I've got a small number of paths. Um, this is the real sticking point in Monte Carlo, what holds it back from being used in more different applications. In practice, in order to price the option within a reasonable degree of accuracy, the number of paths required can be enormous, potentially in the millions. Wow, even the most powerful computers could take a while to come up with a single price. You can see for this reason. Well, for one thing, I forgot to mention this before. Monte Carlo simulation works very bad with American options. It does a good job with European options, but takes an extremely long time. So why would you bother when you've got black holes? Therefore, is often reserved for exotic options when the others would not be very appropriate, where other methods appropriate. Even if they were faster, they wouldn't get as advanced. And of course, that's what matters. Wow. So this is what Monte Carlo is all about. Now, the big issue here is where are these paths coming from? That's where all the math comes from. And this is where you need to do it in such a way that's consistent with the Black-Scholes model. But, in other words, if you notice these paths, there's an assumption that there's a bunch of time steps in between. The path isn't going directly from today to time t. It's stopping. We stop along the way. We have new results. It's one of the reasons why it takes so long. Imagine this is only 4 paths. Imagine if I needed 4 million paths. Okay, you kind of get the idea here. So this is what Monte Carlo is doing. So now what I'd like to point out here is that now since we're getting so desperately short on time, it's really sad because there's so much more fun material that we can do here. I found a second assignment that we can do, but first I want to point out, let's go back to um, Blackboard. We're going to do this. And one thing I also noticed that when I was trying to download these files, I noticed that the Excel spreadsheets were refusing to let me run the VBA components. So what I did here is I wrote this document called Delta code. And what you're going to see here is the VBA code that calculates the price of, the value of a delta for a European call option. So this way, if you can't open the file directly, you can copy this into a module, right? And you can see it's right there. And but this is coming from hmm, here it is. No, that's not it. Looks like I didn't get it in there. Hold on 1 second. Um, yeah, just in the off chance, because what I was trying it before, it just kept saying, no, no, I won't do that. I won't do that. Sorry. Um, he said, was concerned that there's a safety issue, but let me at least make sure that the code is in there in case you're able to open it up. All right, hold. It's from the Black Scholes section. Black Scholes in the Greeks. There it is. I called it Delta assignment and I never put it up. Okay, I'll do that right now. What it is, it's just the same code, except that it's actually in the spreadsheet. So it could save you some typing if you can convince it to work. If not, you got it right here. Now, what's the point of this? What I would like you to do is take that code and rewrite it, and it will only take a very minor change to calculate the delta of the put. Okay, in other words, this one involves a call, and there it is, using the program function called delta. From the spreadsheet, Black Scholes delta, write a function called put delta. So in other words, go in there and create another module called put delta, and it's going to be almost the same as the call delta, but there's some important differences. What you're going to do is rewrite it and then run it on the same spreadsheet. The call part, you can execute the call. And by the way, even if it doesn't let you look at the VBA code, it'll still let you look at the spreadsheet and show you what it looks like. So this won't take very long. Okay, if it ever opens up. I said if it ever opens up. Oh, I apologize. This is the wrong one. And you can see it might do this. This is what I'm concerned about. Nope, sorry, that's the wrong one. It's supposed to say call delta assignment. I just clicked on the wrong one. Let's try that again. No, it never, you know what it is? It never made it into the downloads. That's what the problem is. Um, unless it's up here. There it is. All right. So when you open it up, now if it gives you this crap, don't just ignore it. Just try it again. I don't know what that's all about. It's just it gets like that sometimes. Just try it again. No, yeah, it has, I don't, see, the thing is, there's nothing, I don't know if there's anything we can do to stop it from doing this. But if you try it again, it usually works. If you just keep at it, this is so ridiculous that it would act like this. And it won't open. I mean, we do have the code. That's the bottom line. But I wanted you to show you how the oh, for God's sakes. All right. This is why we have to do it separately. All right. All I wanted you to do is this. Um, well, if it's gonna be like this, I'm gonna have to tell you what information to put into it. All right. Let's see. Let me go get that document that I gave you. Delta assignment, not that one. The Word document that has the code. Here it is. Because clearly this is not going to work. Let me just show you the numbers you were supposed to use. Anyway, the whole idea is to take the numbers I'm about to give you. You should practice it. You should write this into one of the modules and run it and make sure it's working. Okay, with the following data that I'm about to give you. And then when that's done, take another module and copy this into it and then make whatever changes you need to turn it into put delta. Okay, so if you go back to the slide, you'll see the relationship between the two is very simple. Uh, okay. And that even open or what? So anyway, because the spreadsheet refuses to open, which I guess I should expect because technology always lets us down. All right. So just to make it crystal clear, this is your function, but the numbers you should use are these. And by the way, these are the same ones. We've seen these examples many, many times um, throughout the slides. Let's go back to the Black Scholes slides. And this is like the first, or actually the second one that we, no, actually it was the first one we did. You recognize the numbers as soon as you see them. So when we first started doing blush holes in section 6, it's this one, what I call Black Scholes example number 1. Right here. So in other words, you need this information to solve the problem. Actually, let me do this one slightly differently. That should do. All right, you should be able to read it there. All right. So now I would like to point out to you though, and just as a quick reminder, delta, the call delta is equal to ND1. The put delta is ND1 minus 1. So the code up here creates call delta. You're going to just make a very simple modification to turn it into an put delta. Okay. So that's what I wanted to point out here. So I'm going to save this with a new name and put it back on your blackboard so you can read it, even if the spreadsheet refuses to open. And then so what you're going to do is go in there, open up a module, copy the code for call delta, run it, make sure it works, and then write your own code in the second module for the put delta. And just keep in mind that the two are very, very similar. Very similar. It couldn't be much similar, more similar, but at least it gives you, again, a sense of how to run a VBA program, how to create a function, how to execute it on the spreadsheet. So it's good practice. So let me, what is it here? All right, I'm going to change the name to call Delta Cold with data. That way there's no doubt in your mind what it is. All right. So now I can go put it back into your Blackboard, and then you should be all set. Now remember, everything needs to be done by Sunday night. So I might come up with a third problem to work on. I'll let you know tomorrow morning. It's very difficult to do a class like this during the summer because you're learning all the wonderful new information about financial mathematics, but you're also trying to learn a programming language. So it's a little iffy if we have time to do both. But anyway, so let's go back here to Blackboard and replace this one. I'll just delete it with this one I just created. Actually, no, I didn't put it there. There we go. All right, and that's that. Also, I realized afterwards that I neglected to post this Monte Carlo material, so here it is now. Um, this is the spreadsheet we are just looking at with exotic options. This is the code. The code is it's pretty interesting, but there's a lot of new things in there we haven't seen. Also, I just realized that the actual notes are missing. Let me get those out. And then we'll be all set, at least for now. Maybe there'll be one more, but that's it. It will be very straightforward. And then we'll be done. I think the problem is that the Zoom is wonderful as far as it goes, but it really must be swallowing up all of my memory on this computer because it is just as slow as molasses right now. All right, I'm just gonna copy the last file I need is gonna go into the Monte Carlo and then we're done. Oh my God, it might take 20 minutes, but I'm gonna do this. All right, I think we're good. All right, so yeah, I'll see. We'll have at least one more session, just even if it's just to let you know that we're completely done. But um, at most we'll cover one more topic, maybe. We'll see how it goes. Plus, but we'll have to wrap up our discussion about the assignments. I was hoping to have at least one more, but I'll let you know tomorrow how that's going to work. So remember, everything is due on Sunday night, and then so far we have the two of them, and then we'll be done. All right. So I'll see you next time.